Zoom out. Can I zoom in and zoom out? I can't zoom in and zoom out. Oh, yeah, now it's okay. Thank you. All right. We are on to chapter 6, or lecture 6, if you like to call it. And we have devoted 2 lectures to studying coherence transfer in homonuclear spin systems. That is proton-proton, basically. But whatever we said about homonuclear correlation in proton-proton experiments is applicable to any other J-coupled homo systems, like fluorine-fluorine, if you have, for example. But if you have a 1 carbon and 1 proton system, then also we have seen one type of 2-dimensional NMR experiments, that is the J-resolved 2-dimensional experiments. Now we are on to correlation experiments. So carbon-13, basically carbon-13 proton, but can be nitrogen-15 and proton, which is becoming very useful in recent years. I would basically talk on carbon-13 proton, but it is equally applicable to other rare nuclei. There are basically 2 problems on carbon-13 NMR. That is, one is to enhance the sensitivity, and that could be enhanced, for example, by nuclear Overhauser effect. And in a conventional way, in a 1-dimensional NMR way, we basically do that by saturating the proton magnetization, which then transfers magnetization to carbons, and we detect them, say, for example, under decoupled condition. The other possibility is of relating and finding out which protons are coupled to which carbons. There are, again, 2 ways of doing that. For example, you can do a selective nuclear Overhauser effect experiment. That is, you selectively pump at the proton frequency of one of the protons selectively, and then observe the carbons under decoupling condition. The proton that you have pumped at, and the carbon that is directly coupled to it, relaxation coupled to it, would get enhanced intensity. And so you could then identify 1 by 1 various proton-carbon pairs. This was a conventional way of doing this experiment. Another way of finding out which proton-carbons are related was to do what's called a CW or broadband decoupling experiments. The previous one is a selective nuclear Overhauser. The second one is a selective decoupling experiment. Or for example, off-resonance decoupling is a type of selective decoupling experiment where you could really point out where you are irradiating and which carbon is related to which proton.
Do we have this page?
No, you do not have this page. This I wrote up as an introduction afterwards, just this afternoon. This particular type of experiment, the type of decoupling type of experiment, is basically replaced by transfer of population through J-coupling. There are several of these experiments that have been developed which are more or less offshoots of 2-dimensional NMR, but one can do them in 1-dimensional NMR way. So in this particular case, then 1-dimensional NMR and 2-dimensional NMR are interchangeable. And we then come to what's called heterocozy, or heteronuclear correlated spectroscopy. Heteronuclear cozy, to understand heterocozy is rather straightforward. This is the first page that you have, and it is basically an experiment which is similar to homocozy, except that what you're doing is slightly different. Suppose you had carbon proton suppose you have 2 homoprotons, 1 and 2, and you ran a normal cozy. We really had not distinguished in the homocozy experiment whether these are hetero or homo spins, so long as we applied the pulses on both of them. Now, if you could somehow apply pulses separately on those two coupled protons, then we would have a heterocozy. Okay? And then if we think of that's the same situation in this context here, we apply a 90-degree pulse on proton, or one of the two protons in the HOMO experiment, and then this is a T1 period, and then apply simultaneously or one after the other, it doesn't matter, pulses on both the proton and the carbon. Then what we would have an equivalent of a homocozy would be that in the T1 period, or the omega 1 period, we would have excited one of the two spins. That means proton spins. So we would not excite the carbons. We will not see this part of the spectrum. Okay? And while detecting, we only detect carbon. And we do not detect the proton. So we will not detect the proton. We will only detect the carbon in this omega 2 direction. And so we end up with this particular portion of the two-dimensional spectrum. So the similarity between a heterocozy and homocozy is total. What we have done, we have only excited one of the two nuclei during T1, and we have detected only one of the two during T2. If, for example, we had applied a 90-degree pulse to carbon also, then we would have both proton and carbon frequencies in T1, and we would basically look at this part of the spectrum. We'll have the diagonal peak of a carbon. But the diagonal peak of carbon will be missing in this experiment, and we will have only the cross peak between the proton and the carbon. And that tells us that that particular proton and carbon are coupled to each other because they exchange magnetization. And this cross peak has antiphase plus minus minus plus character. And so basically that's what we should get. And indeed, if you look at the result of a very simple one carbon coupled to one proton result, this is what you see. There is an antiphase character. The J coupling JCH appears in both the directions. There is also in this particular case an axial peak, which we know can be cancelled by a phase cycling experiment. And so we need not worry about the axial peak. We only look at the other one. When we look at this spectrum, it has information that we want, that which proton coupled to which carbon, if we had a chemical shift information and a number of other such cases. But immediately it becomes apparent that it would be nice if we could decouple them. Okay, and so we will then only need the chemical shift type of information, and this can be done in various stages. For example, in the very first stage, you may just like to decouple in the omega 2 direction. But yes, you can decouple, but remember, these are plus minus intensity character. And if you just decouple, they will overlap and cancel. So before they overlap, you have to do something and bring the antiphase intensity character into in-phase. And we already know a recipe for that. In fact, the recipe that we used in homonuclear came later, and this came earlier, and people had devised these experiments before we did this in homonuclear. So we borrowed the idea from here. The idea was already existing. In heteronuclear case, they wanted to do decoupled heterocozy, and so this antiphase character had to be destroyed before they could decouple. And so you throw a delay and put a pi pulses, which are not necessary if you're going to do an absolute intensity plot. Okay. So the pi pulses are optional. If you can maintain phase purity, then they are useful. But otherwise, they take away the chemical shift precession from this delay period and make it only effective for the coupling. Again, we have to make this period having a relation that the total period should be equal to 1 upon twice J CH. Okay, and so the result would be that you would have a decoupling in omega 2, but coupling in omega 1. All right, and this is the result of that experiment. You can do decoupling in omega 2 and coupled in omega 1. You can also finally decouple in both the omega 1 and omega 2 directions. But the omega 1, omega 2 decoupling, then the scheme is fairly obvious. Sorry, what I have here is another scheme in between. Okay, maybe I should then come to this fully decoupled spectrum later. A word about how much is the value of the delay. And the value of the delay is dependent on whether you have a CH group or CH2 group or CH3 group. And because if you look at the spectrum, of carbon spectrum, then it has a doublet, triplet, or a quartet, depending upon you have a CH, CH2, or CH3 group. And so there are various frequencies of these resonances. For example, in a doublet case, in CH case, they are plus minus half J. In this case, there is two transitions at 0 frequency and 2 at plus J and minus J. So, and CH3 has transitions at plus minus half J and plus minus 3 by 2 J. Therefore, the frequencies in your procession of these magnetizations are half J, J, half J, and 3 by 2 J. And therefore, the time dependence, the amplitude dependence of the amplitude of these precessions are functions of these delays and J values as given in the notes here. For example, they are given by sine 2 pi J by 2 tau, sine 2 pi J by 2 J 2 tau, etc. And these are maximum for CH case for tau is equal to 1 by 4 J. Please remember that I have defined tau as 1/2 of here and 1/2 of here. Very often people in books and in journals write this total period as tau. And so sometimes you have to be a bit careful whether the talking about the full period or half of the period. Okay, so 1 by 2 J or 1 by 4 J or 1 by 8 J, less than 1 by 8 J. This is maximum. You can see I have plotted these functions that I have written down here, and they look like this. The CH group as a function of tau will have this behavior. This thing is plotted here as a sine curve. Then there is a sine cos curve, which is nothing but sine twice the sine curve. It has twice the frequency. And then we have a sine cos square curve, which has this behavior for the CH3 group. If we wanted all of them, it would be advisable put our delay at this point. So we'll get some intensity for all of them. If we want to do what is called spectral editing, we can put our delay at this point, and you will notice then what will happen that the CH group will show up, and the CH2 and the CH3 groups will not show up. If we wanted all of them, but wanted to have some additional information, we could put our delay somewhere here. Then we will see that the CH and the CH3 group will come with positive intensity, and the CH2 group will come with a negative intensity. And so with these delays, we can do what is called editing. We could also find out whether it's a CH group, CH2 group, or CH3 group, along with the chemical shift information. Okay. Well, one can also do decoupling in omega 1 direction. And the scheme that is given here is omega 1 decoupling. And this can be done by two different ways. One is by simply irradiating the carbons during T1 period. It's opposite to what you're used to doing. You are used to irradiating the proton and not at the carbon frequency for decoupling purposes. And some of the spectrometers, you may not be able to do this. Okay. Then there is a simpler way of doing it, that you simply put a pi pulse in the middle of the carbon precession period, in the T1 period, assuming weak coupling in protons, this will decouple. Okay. Basically, the J, I, Z, S, Z has a SZ term which is changing sign. And so for half of the T1, it is processing with plus half J, and for the other half, it is processing with minus half J and causes focusing. But It doesn't cause carbon-13 chemical shift. It will also cause carbon-13 chemical shift, but we are not looking at carbon-13 chemical shift in this direction. We are only looking at proton chemical shift, which is not affected by this. Okay, so that's how the pi pulse on the carbon works. And the rest of the scheme is straightforward. All right, you can then this comment refers to number 4. Okay. This comment here is actually for the lower case. We will see why it is so. All right, but let's see. Now if we want to do decoupling in both the directions, we can do that, but we will have to bring the antiphase component. Oh, I'm sorry. It does refer to the previous one. Sorry. Notice the difference between 3 and 2. There is a very important difference between 3 and 2 sequences. The delay period in 2 is after coherence transfer to carbon-13. Okay? While this delay period is before. And so it is to bring the omega-1 components in phase. Okay? And now how much should be the delay? And this proton is always a doublet. The proton spectrum is always a doublet in the CH2, CH3 cases with the splitting of J. Therefore, this tau is not dependent on CH, CH3, and CH2, and is always be the same. Okay, so this is okay. I should call this T1, this T1, and then this is for both. Okay. So this is clear. And when we go to both, decoupling in both the dimensions, we combine the two. We do a delay in T1 period as well as in T2 period. The tau2 will follow rules that we gave for omega-2 decoupling, and tau1 will follow the rules we gave for omega-1 decoupling. Okay, and one can get a decoupled spectrum, as I showed you here, which is then is a single frequency telling us that on omega-1 axis, that's the proton frequency, and omega-2 axis, that's the carbon frequency of that particular carbon. And you can immediately see its utility, and it is a very widely used experiment. And you can see, for example, an example that has been given to you. That one can then relate various carbon sites to various proton sites, frequencies, and this helps us in assignment as well as in confirming our molecule that we have synthesized, for example. And this is the, you will notice one or two things. Let's see that there is a slight broadening in the omega-1 direction. In the proton frequency, and I will come to it later. On this transparency, I have what we call as an analysis of heterocozy experiment through what we should call as a product operator method. A very small one I have here, and I want to emphasize one point, and that's why I'm going to go through it again. Basically, we have done this for homonuclear, but since I want to emphasize one point, I would go through it again. At point number 1 in this sequence, we have an IX operator. That is the proton magnetization in the X direction. Okay, after the application of a 90-degree pulse. And then this evolves under chemical shift as IX cos chemical shift T1 plus IY sine chemical shift T1, which under J coupling, the IX part of it has IX cos pi J T1 plus twice IY sine pi J T1. This is because the sine term gives us a 2ISZ outside. Okay, and cos. And similarly, the IY will have another part of the evolution which we don't need to worry about at the moment. Now this term is what it is. This is the term which says that the proton magnetization at point number 2 before the application of the pulse is an antiphase character. It has two components, one up, one down, in the Z direction. This is the, in the xy plane. In the xy plane. This is the meaning of this operator. Okay, then we apply a 90-degree pulse along x-axis on the I spin. And that converts this IYSZ into IZSZ. That means this particular magnetization of the I spin, which was in xy plane like that, is converted into a z direction, plus half and minus half. And then when we apply a S pulse along x-axis, it appears as a X magnetization, which is antiphase in proton way. So we get a IZSY, which is detected. Okay, the S magnetization we get. We can think of it slightly differently. Well, I don't have to, these two pulses actually commute with each other. I can apply any one of them before or after or simultaneously. It doesn't matter. So let's see what if I apply the S pulse on the IYSZ state, that is this state. I apply a carbon pulse first. Okay, then I will convert it into something which I cannot show by vector diagram, but it will look like a IYSY, which is actually a double quantum and zero quantum coherence of I and S spin. And I cannot describe it by a vector diagram. We will come to that in subsequent lecture. And then I apply the pulse on the I spin, and I get exactly the same operator back as before. So the end result is identical. We could not see this state in the homonuclear case simply because there was only one pulse. We applied at both the spins at the same time. Here we have the facility to apply one pulse at a time. But these pulses commute. Therefore, the result should be the same. Okay, and that's what it is. And this is called a longitudinal two-spin order, IZSZ. A longitudinal two-spin order. And this is called a zero and double quantum state. And these are very interesting ones. We will see some of these in a multiple quantum transition lecture, and later on in another lecture in which we are going to look at longitudinal coherence transfer via longitudinal spin order, where we will focus on terms like this. Now, if we have only a carbon coupled to a proton, it's fine. But these protons are often coupled to each other. And this can create difficulty. So we have, for example, a carbon coupled to a proton, which in turn is coupled to another proton. As well as this carbon may be coupled to this proton through what's called a long-range coupling. But at the moment, we want to focus on this proton-proton coupling. And what happens is this proton-proton coupling gives rise to